think my shirt.
That's okay. You can just bleach it. I'll show you.
Okay.
Let's put on gloves because bleach can irritate the eyes, skin, and lungs.
Wait, so what do? Do we just pour the bleach onto the shirt?
No, we're gonna first mix a cup of water for every half cup of bleach so that the bleach solution isn't too concentrated.
Okay. So now what do?
We're gonna take the whole shirt and we're gonna submerge it in the bleach solution for 5 minutes.
Okay.
It's been 5 minutes and you can already see that it works.
Wow.
We're just gonna like rub out some of the stain and then we're gonna wash it in the sink with soap and water.
Okay. Wow, that works so well. But like, how does the bleach actually work?
That's a really great question. Let's zoom in on a molecular level and look at what happens.
Okay.
Wow, what's that?
That's one of the molecules causing the stain. In this case, it's from the food you spilled on the shirt. This molecule is a conjugated pi system, which means it's a long chain of carbon atoms with alternating single and double bonds.
Got it. So that means that at each carbon atom we have an unhybridized p orbital?
Exactly. Most of the time we have sp2 hybridization on each of the carbon atoms, but technically it doesn't have to be carbon atoms. As long as each atom has an unhybridized p orbital, it's part of the conjugated pi system. We end up with a system of overlapping p orbitals, and these form pi bonds that are delocalized over the whole molecule.
That's cool, but what does that have to do with the color of the stain?
Well, this molecule is a chromophore, which is what gives the stain its color. Essentially, the molecule can absorb certain wavelengths of light exciting electrons in the conjugated pi system. The smallest difference in energy is between the HOMO, which is the highest occupied molecular orbital, and the LUMO, which is the lowest unoccupied molecular orbital. So, when energy is absorbed, electrons in the HOMO are excited to the LUMO and then fall back down to the ground state, releasing energy. The color we see is determined by the absorbance spectra. That is, our brains see the color complementary to the wavelength absorbed by the molecule.
So how does bleach remove the color of the stain? Does you use intermolecular forces to remove these color-causing chromophores the way that soap removes dirt?
Not quite, but that's a good guess. The bleach we're using is sodium hypochlorite, NaClO, which is an oxidizing agent, meaning that it removes electrons from the molecule. By oxidizing the double bonds, it breaks up the conjugated pi system because we no longer have a system of alternating single and double bonds. As a result, the conjugated system is shortened, meaning that the HOMO-LUMO gap increases and the molecule only absorbs higher energy light. Since we can only see wavelengths of light in the visible spectrum, anything higher energy like UV light is invisible to the human eye.
Oh, that makes sense. So the bleach breaks up the conjugated pi system into smaller conjugated pi systems that only absorb UV light, meaning we don't see the absorbance spectra and the color disappears.
Wait, I'm still confused. Why does a smaller conjugated pi system increase the HOMO-LUMO gap?
That's a great question. It all goes back to the idea of a particle in a box. We know that a particle in a box has energy determined by the equation En equals n squared h squared over 8ml squared. If we think of the conjugated pi system as the box, since all of our pi bonds are delocalized over the whole molecule, and the electron is the particle inside of it, shortening the conjugated pi system is essentially decreasing L, the length of the box, which will increase the change in energy for different values of n. Therefore, we need more energy to excite an electron from the HOMO to the LUMO. This higher energy corresponds to a shorter wavelength of light, like UV light, which we can't see.
Oh, I get it.
I wonder how my shirt is doing.
Let's go check.
Wow, it looks as good as new.
Yeah, and you're lucky it was a white shirt, because if it had been colored, then the bleach wouldn't discriminate between the dye of the shirt and the dye of the stain. So it would actually fade the color of the shirt.
Oh, okay. I'm so glad my shirt is okay. Thanks for your help, guys.
In summary, first, stains have chromophores. These are conjugated pi systems with delocalized electrons that can absorb specific wavelengths of light. That absorbed wavelength determines the HOMO-LUMO transition, and the size of that energy gap tells us exactly which wavelength gets absorbed, and therefore which complementary color we end up seeing. Now, the length of the conjugated system really matters. A shorter conjugated system has a larger HOMO-LUMO gap, which means it can only absorb higher energy light. And once the absorbance gets pushed into the ultraviolet, it's outside the visible spectrum, so we can't see it anymore. This is where bleach comes in. Sodium hypochlorite is a strong oxidizing agent, and it breaks double bonds within the conjugated pi system. That splits one long chromophore into several shorter segments with much larger energy gaps. As a result, the stain doesn't actually vanish. The molecules are still there. They just stop absorbing visible light, so to our eyes, the color disappears. And finally, because bleach is non-selective, it will oxidize any chromophore it encounters. That includes the dyes in colored fabrics, which is why bleach causes fading unless the fabric is white.
Wait, so now.
Are you time-lapsing it?
No!
Okay.
I probably should have been, but
We can like manually.
is that a, can we retroactively time-lapse a video? Is that a thing?
Speed it up. That sounds like Grandma Blonde.
That's what I'm saying, like the chlorine.
Wait, oh my god, sorry.
Whoa!
Well, that's crazy.
I totally expected it to actually work. Wow.